Hello everyone. My name is Priyakshi, and on behalf of EV Reporter, HBK World, and Discom by HBK, I welcome you all to this webinar on sound and vibration considerations for electric and hybrid powertrains. We hope that today's technical presentations will provide you with valuable insights. Let me quickly take you through the event agenda. We will start with a short introduction to HBK from Prakash Stephen, Director of Sales at HBK India. Then we'll move on to our first technical presentation on why sound and vibration is key for electrical motors. This presentation will cover some challenges, trends, and examples of simultaneously measurement and data analysis of electrical power SNV. Marjorie Takai will make this presentation. She is an electric powertrain specialist at HBK World. She studied physics at the University of Sao Paulo and continued her studies at the University of Tokyo, where she completed her master's degree in acoustics. It's the field where she has been working since 2009. Later, she joined the EPT team as sales specialist for the APAC region. Welcome, Marjorie.
Thank you.
Yeah. So glad to have you. And after Marjorie, we'll have Alex Balvedi presenting on achieving acoustic quality assurance in production, tackling potential noise complaints in automotive powertrains, as well as current state of art of end-of-line acoustic production testing. So Alex has over 20 years of experience in automotive and oil and gas industries in various leadership roles. In 2018, he joined HBK in Germany. And after leading the global sales team of HBK's division Discom, Alex relocated to Japan to support HBK's customers in the APAC region. Alex holds a doctorate in mechanical engineering, focusing on sound and vibration. Welcome, Alex. We are glad to have you.
Thank you. Happy to be there.
All right, so let's get this started. Towards the end, we'll have a Q&A session. So any audience members who have any questions regarding the contents of today's presentations can use the Q&A box to submit their questions. So let me now invite Mr. Prakash Stephen for an introduction to the company. Over to you, Prakash.
Thank you, Priyakshi. And thank you also, Ashish, for giving us this opportunity to present our products, as well as talk to you about on the sound and vibration, as well as end-of-life testing, which can be done with our products. Yeah, so without going further, let me share my screen. Oh, my screen is visible?
Yeah.
Okay. So myself, Prakash, I am the Director of Sales as well as the Country Manager for HBK in India. So who is HBK? And what's our mission and vision that we go along with? So our focus is for customers as innovators. We empower the innovators by providing exceptional insights with our sensing capability and help them to create solutions for a cleaner, healthier, and more productive world. That's our mission and purpose for the company. HBK is a global powerhouse across test and measurements, simulations, and analysis, bringing innovations to our customers for more than 80 years. We are spread across 50 plus countries with 800 plus customer facing employees and 300 plus in R&D, where almost 50 of them are stationed in India itself. Our sales in 2023 globally was around 637 million euros and 11 million in euros for India, which is approximately 2% of our global turnover. HBK is very bullish on increasing this percentage in India, and we see it as a growth area for us. The business operates from a single site in Chennai, where our sales office is. The software development is also here, and we have our testing center also in our Chennai office. The sales staff work remotely from home offices in key locations, industrial areas across India. HBK is your partner through the entire product life cycle. We want to add value at every stage of development, production, and asset monitoring. We want to close the gap, which is there between the virtual testing as well as the physical testing, by closing the V development cycle in an automotive industry. And how does this help? This will help people move towards, or company move towards, zero prototypes and accelerate innovations, bringing products faster into the market. So these are our main testing areas by providing complete test and simulation offerings. First is we divide our product portfolio into two processes, which is R&D and in-process. And in R&D, we have the virtual testing, where example of our hardware in loop for driver simulations of track and NVH simulations. So this leads to zero prototype testing. And how do we do it? It's not simulation or complete virtual simulation, which is there, but physical testing is a requirement. And we have precision products, reliable sensors covering key physical properties, almost ranging from electrical, torque, force, pressure, displacements, data acquisition, high precision data acquisition systems, which help in gathering this data, and software, which gives you insights for user-friendly reliability testing and analysis. Coming on from the R&D, once you have done your R&D, it gets into the production process. We have sensors built into systems where they can be used to bring actionable insights for precise and smart sensing. These are reliable sensors with high precision, with EMI proofs, explosion proofs. So this goes into the product on a day-to-day basis usage. The other part would be the production itself, coming on to it, where we rely on other high precisions, intelligent signal conditioning, mostly for your end-of-line test systems, giving you insights into the production, looking at the trends and faults so that you would be able to correct them. So that's our complete offering as such. 2024 has been a very exciting year for us, where we have brought in a lot of innovations into the market, going right from your top left-hand corner, where we have brought in our fusion probes, which are specifically what Marjorie is working on today. And this is especially very useful where there is high voltages and high EMIs, which are there in your electrical vehicle testing or motor testing. Then coming on, we have to the data acquisitions side, we have our eDrive software and hardware, which help you collect these voltage accelerometer data and NVH data into one single source and help you analyze. So these are some very important new products that we have brought into the market. And to those people who are already using a lot of other data acquisitions and other for different DACs, we have also got in our open DAC architecture, where it helps to interface all the different DACs on a common architecture so that you could pull in data as and when required from the different data acquisition systems. So that's our open DAC platform, where lots of other companies are joining us to bring this out. And of course, on the software side, we have the Relia software where we talk about the reliability testing, so which helps you in talking about the warranties that you have to give the customer to analyze what is the kind of warranties, what is the kind of reliability of components, as well as your complete product as such. So that's on the side of the data acquisitions and thing. Coming on to the sensing elements itself, we have now IO-based intelligent digital sensors, which give you direct information kind of plugging on into your PLCs so that you could have information as and when required to do corrective actions. So that's some of the products that we have brought into the market this year. So without holding more, I would like to pass on to Marjorie, who would be able to talk to you more on NVH in electrical drive systems. Marjorie, on to you.
Thank you very much, Prakash. I will start to sharing my screen.
Yes.
So hopefully everybody can see it. So
Okay.
thank you very much, everybody, to attending our webinar. And I will do like the first part of it, and my colleague will do the second part. So my focus will be on the R&D. So, and my colleagues will be like on the end of line side. So thank you very much for the introduction. So I think I will start here. Everybody talked about like the background. One of the things that I just wanted to emphasize, like I've been working with the motor side, electrical motor side, but my experience is the sound, like a sound side of it. So I've been working with sound since 2009. So it's been a while, and I've been working with different parts of it. So I think that we can bring this experience from the sound world into the motor world as we see the things are transitioning to the electrical side. So why should we care about the acoustics, noise, and vibration? Here we'll talk about two aspects of it, and here in the images, we are looking to like the passenger's car as an example, but could it be anything? Could it be anything that has an electrical motor? For example, fridges or small appliances to big ones. So here is focusing on the customer experience of it, and that's like the outer side of it. So when using a car, for example, what you're expecting from it, you expect some comfort. So when you're riding a car, you expect to have like a pleasant experience. So, but unfortunately, we as human beings, we are tuned to notice some stuff. For example, a child crying can be a little bit annoying, and it's not because it's made by nature, because we are tuned to hear like a higher frequencies to pay attention with this. So it's the same. We use this design in our world as well, in the sense that sirens for ambulances, police cars, they are in the higher frequencies. So we don't ignore this. So we use this type of like our characteristics as human beings to design the sound that we have around us. So it is part of like how the customers wanted to experience our products as well. However, we don't have like only the side of the customer experience, but we have like about the noise requirements, noise standards, and it's local. Can be different for different parts. Some of the countries have agreements, but we do have noise requirements, and they may include environment impact as well. So how much noise we're generating and throwing into the environment. And some of the things that are common for both sides is that we have some expectation. So we expect that our cars sound as cars, or that we enter our kitchen and our fridge sounds like a fridge, not a hair dryer or like a washing machine. So we have expectations, and some people, they actually use the expectation and break it. So they use, for example, for hybrid cars, some companies, they use this very particular type of noise as branding. So they branded themselves as innovative because they have this sound. So we have like the expectation, the branding, and this adds value to the product. So when you're riding an expensive car, you expect that you have comfort, you expect that you're not be annoyed by small sounds like vibration from the glove compartment or things that are not done well. And it's the same as well if you don't pay a lot of money, but you feel you have the feeling that is well done experience, like you have a good experience from it. So that's one of the things. Acoustic signature of a vehicle or any product can be a person's criteria. So we make decisions based on what we feel and how we experience the products. However, in the sense if it's small or big, expensive ones. And a lot of it is how we design this and how we deal with the things and characteristics and how we brand our material, like our products or not. So, and one of the things like how it does it apply for like electric power drives? How does it apply it for motors, electrical motors nowadays? One of the things that I see very commonly is that we have like the motor development. You develop the inverter side, and after you do everything, you throw to the SMV NVH team, and they do the measurements. But what is the benefit that we would have if we do both at the same time? Before answering this question, I will go through some of the mechanisms of, not mechanisms itself, but some of the causes of the sound and noise vibration that we have in electrical motors. Very briefly, it's just introduction, so we can go through the problems. So one of the things is that the constitution of the motor itself. When we excited the motor, because we wanted to make it rotated, and we are not, we don't have like linear, like everything is not done linearly. We ended up like, because any body wants to keep in movement, it will have, and but we block it. We have like this cog and torque that is shown here, and this ziggy line here. We have like the potential and it will induce movement, but we are trying to control this movement. So it will have like an opposite force. It will have like an impact on how this output happens. So that's one of the things. Like the motor constitution itself will generate some of the sound, the noise, and the vibration when we excite the motor. Because torque follows excitation, like. And secondly, is the inverter. Here we have a schematics on showing the battery, the inverter, and the motor. Of course, we don't connect the battery directly to the motor, otherwise we wouldn't have movements. So when you do this, like the inverter has a role of controlling the motor. And when you do this, we ended up like having like a square waves. And what it does, like it's a very short thing here. When you have like a square wave, it can be decomposed in sine waves. That's the Fourier decomposition. And we have like harmonics of the main frequency. So what it does, it injects a lot of harmonics into the system. And what it does, it affects the torque and the end. So the inverter affects on how the torque output will be. For example, like in here, we have like the, oh, sorry, here, I didn't see it. The inverter currents are not ideal. So it will inject some of the torque ripple and the system. And I will talk a little bit about it later. So how we control the motor makes a lot of difference. Here we have like two systems, like two examples. One is like PWM and a 6-step control technique. They look kind of similar-ish in the shape, but how it's done makes all the difference. Here we have like the current gone to the motor. So in the PWM, we have this sine wave, but in the 6-step, we have like these peaks and dips and the signal, and it makes all the difference in how the torque is outputted. Because here in the PWM, we have like a kind of sinusoidal wave. We do have like peaks and dips, but they are not as prevalent as here in the second case. So the inverter control affects directly the output of the torque. So what is the second mechanism like that we are talking like broadly here? So the motor constitution and then how you control your inverter that's feeding to the motor. And it generates torque ripple. So here is just an example here in pink that we have a torque that is fixed and you do a ramp up here and greenish line. So we start like from low speed and you speed it up. So when you do this kind of analysis, just a side note, we do need some accuracy from the sensor that you're using for the torque sensor. So you need an accurate sensor and you need like a high sample system to acquire this data with the suitable filters. Otherwise, you're just going to flatten out everything and lose all this information. So you're not going to have the torque ripple detail and what's going on. So here we have the torque that is went through the system. And here in the black line, we have the percentage of the torque ripple comparing with the torque that is averaged. Here we can see like, oh, something is going on. Although we don't see, like we are just speeding up. And it doesn't happen in all the parts of the signal. So that's one of the things that can happen and can cause noise and can be investigated. So it's just a reminder that when you're doing this type of measurements, we do need to be, the torque ripple is very small comparing to the biggest of the data. So we do need accuracy for the sensors and the system itself that we are using for the measurements. So when you're doing the measurements, you're designing your motor, you're designing your system, you have like found like you've measured everything, you have like the good like efficiency mapping. As here we have like the torque, and the torque and the x-axis and the RPM and the Y, and the color plot we have the efficiency. Oh, we found like a very good spot to operate the motor. But however, if you do measure the torque ripple, it can like show that actually like a good region to operate can be very bad for sounding vibration. I say that it can be because in this case we didn't measure these two things together, but that's the thing. If you do, what are kind of things that we can check out what's going on? And now I'm going to talk about a little bit of the benefits of having like both measurements done together. So here I have just an example like of a power source, inverter, electric machine connected, and we measure the voltage current from the batteries. Same for the inverter, measure the torque and speed from the machine. Maybe you wanted to measure the temperatures as well from the machine, battery, inverter. Also here in this diagram, I have like the accelerometer, microphone. And here in this example, everything is integrated, so it can be automated. You can do send the data back and check out what's going on. But one detail that is very important, when you're taking this type of data all together, temperatures, vibration, the electrical measurements, the sound from it, you of course can do using different equipments. You can have like different data loggers for things, but if you're going to use to find the cause and like the root cause for things, for the consequences, that is the sound and vibration in the end, you need to have like everything time aligned. And if you have like different systems for doing this, it's a nightmare to align. How do you guarantee that every measurement started at the same time? How do you guarantee that they have like the same sampling rate for the measurement? And that's the benefit of having like a one centralized system to do everything. So we can start doing interesting analysis as checking out how the current affects the vibration of the motor. For example, in this case, we have the FFT, it's a frequency spectrum of the current and the vibration that was measured in the motor. For example, here in black, there's circled here. We have like the rotational frequency of the motor showing the influence in the vibration. Also, we can see like the inverter switching frequency has some influence in the vibration as well. Of course, the values are not going to be the same identically because the system is going through this, the current is going through the system. It will have influence, but it will have like a different characterization of it. Of course, but still, we can start to look out for what causes the noise, what causes the vibration from the electrical side. Also, we can start looking at how the torque, how the load of the system affects the vibration of the system. As here we can see, like when there is no load, it's very different when we have load on the system. It's already like something to check out. And if we have different loads, we have slightly different frequencies. Some peaks, for example, in the 26 nanometers, we have some peaks that we don't have anywhere else. So there are some special frequencies that will have some more noise than others because of the motor constitution and how we excite the motor. So when we start to have like this kind of data aligned, we start to see some cause and consequence. So it's like we can try to search for more for the root cause and prevent it and the cause, and not spending time and money trying to mitigate it after development. And not only, because I was showing some examples for the vibration side, we can do for the sound as well. Here we have like a little bit different type of information. We have the frequency of the sound, and we have here the speed of the motor. And the color plot shows the sound that was heard in the left ear inside the car for the two different motors. As I said in the previous slides, different motors have like different types of sounds. And I think my colleague will talk a little bit more. And we can use this information also. But we can see that how different it is and how loud it becomes depending on the speed that we are. And we can use this for simulations. We can use harder in the loop to check out and how it will sound when you have actually running on a road. We can simulate before going to market, before having prototypes. And also we can start to use this information because we have like both information here. We have like the noise information and we have the electrical. We can check out like and decompose like the cause of the sounds. Here for the different type of motors, we can separate the radial forces from the torque ripple that causes the contribution to noise. And here, although like they have like from the torque radial forces, they have like a similar inclination of the curves, they have very different torque ripple characterization. Where we have like in the orange one, we have like in the lower frequencies, we have like higher and then lower levels for the sound generated. We have like higher levels for the radial force and like the torque ripple and the switching reluctance motor here. So we can start to see, check for patterns and check in ways to mitigate these causes and reduce or choosing what to compromise in the developing stage. So we don't have to spend money and countermeasures later in the process. So yes, this peak here and how loud it became inside the car. So we have like tools that can allows us to analyze data in a different way. And we saw some of the FFT data. Now we have like some spectrograms. Here we can see how like here in the first line we have like currents and then we have the vibration spectrum. We can see like how it correlates to the orders of the motor and here the orders and how it goes through the vibration, how it gets in the end, and the relationship that has like with like how we excite the motor and how it responds. And some of them we can check out like, oh, maybe something is going on here. We have like a straight line. So regardless of the speed that this motor is running, we have something going on. So we can start to check this kind of information that may appear or not, but we have the information that allows us to investigate the causes. So again, some of the benefits of having the electrical measurements with the sound and vibration. We can reduce costs. We can do like both of the measurements at the same time. So we don't need to have like one team to do the electrical, develop everything and test it, and then test the sound characterization of it. We can reduce this step. So we can develop it faster. We can mitigate the noise in the control. We can change a little bit of the topology of the motor so we can have less noise. We can have like an easier communication between like teams. We can now use this information faster. So characterize fatigue, failure. And my friend will talk about like end of the line as well. We can start like having this, how this motor will behave and have this information on our hands before going through all the steps until the end of the sound measurements. So what do we provide as HBK? And it's a little bit confusing sometimes because of the nomenclature, but our solution is called a drive. And I know that a lot of electrical drives are called a drive as well. So bear with me. Here, one of the things that we are very proud is that we do measurements with different quantities. Here we can measure voltages, currents, torque, of course, for the electrical characterization, but also include temperatures, like microphones, accelerometers. If you have, depending, like we can check what we can input, but we can input a lot of things in the same DEX system. So it allows like to have information broadly and time align it and in one system. Also, we are fast and accurate. What I mean by fast, we can have like real-time data output. We can calculate some values and give it in hard time, hard real time. We are future-proof. That can have like a lot of meanings, but for us is, for example, if a customer wants to read some data of 30 years ago, they can, because we are very consistent in how we generate and read the data. Also, oh, maybe I'm using a motor today, but I wanted to expand. Will I have to buy another system? No, we can just expand the system that are already there and keep the same configuration for things that needs to have like the same configuration and be controlled by the same computer. You don't have like to have different systems to measure the same thing. You can expand. So if you are measuring a motor that has 3 phases, for example, today, but maybe it may expand to 6, 12 phases. I have some customer measuring 12 phases with one system. So he just bought more boards for adding channels to the system. So it's future-proof. Second, audible testing. For example, you wanted to check on what calculation was done at the time. We can open all the formulas and check out what was done. Also, because we can do this, oh, I forgot to add a formula for this one. I can add it later and recalculate based on this. So you don't have to run the test again. You can just rerun digitally, calculating the values. And last, as like one of the main values, like the 5 main values for the HBKC drive is like feedback to control systems. These allows very cool things like test automation, test optimization. We can do hardware in the loop. We can put like simulation in the loop and have like less prototypes. We can be faster in developing our products and help you to develop your products. So that's it for my side of the presentation. If you need more information, that's like from the product side, that's our homepage. For the sound and vibration, we do have like a YouTube channel with a playlist only for NVH. If you like, the link will be in the PowerPoint. And now I will hand to Alex.
Thanks, Marjorie. Obrigado. Good afternoon, everyone. Thank you for having me here and welcome to our webinar. Let's talk a little bit about end-of-line testing, NVH related. I just want to remind you, we have a Q&A board in the webinar. Please feel free to place any questions that you might have. Just make sure that the difficult ones you address to Marjorie. She's the smart one here. Okay. So my name is Alex. I work for HBK's division called Discom. For those who never heard about Discom yet, is Imagine that you design and develop your product beautifully. It's a great product according to Marjorie's recommendations and observations there. Now you go to large scale. You have to produce them on large scale. Discom basically helps you to make sure that these products, once they are in the market, they are not going to come back, or they are not going to incur in an acoustic quality complaint. So that's where we can help you. So why acoustic quality assurance in production? Well, the first is that when you talk about electric cars, you're gonna probably, if you heard them or if you didn't hear them so far in the streets, they tend to be quieter than internal combustion engines. So they are not as loud as internal combustion engines. However, they are way more noticeable. Why is that? Because the acoustic signature tends to be tonal and modulated. And guess what? We as human beings our brains have been trained for thousands of years to pay attention to tonal and modulated sounds. So they are not loud. They don't have to be necessarily loud e-drive systems, but they are noticeable. Unfortunately, we pay a lot of attention to these noises. We also want to find hidden defects. It doesn't. We may not hear a phenomenon inside the car. However, acoustic end-of-line testing may show you some indications of potential issues in terms of durability, or that will eventually affect the lifetime of your product. Some examples are the magnetization of the electric motor or waviness on gears. This all can be shown beautifully on the vibration signal in the end of line. So you also want to have an overview of your production. You are manufacturing hundreds of thousands of units every day. You want to know what's your performance, what's your scrap rate, and why I have such a good production, or it's not going so well in certain days, or whatever. So you want to have an overview of it and gain insight to it as well. So end of line, NVH in end of lines, noise and vibration in end of lines have a broad field of applications nowadays. We literally have hundreds of projects every year dealing with acoustic end of line control for e-drive systems as a whole, transmissions, gearboxes, gear testings, and so on. As a matter of fact, gear testing is a growing market because people are realizing that now that the background noise from electric cars are lower, we start listening also the gear meshing, and manufacturers want to make sure that they are delivering the gears free of noise, free of nicks, free of waviness, micro waviness, meaning ghost orders in the end of the day as a noise. So they want to make sure that they are delivering proper gears to the gearbox manufacturer, and the gearbox manufacturer want to make sure that they are delivering proper gearboxes, noise free to the e-drive manufacturers. So now we have our background noise in the car going down. Guess what? We start listening to actuators and bearings in electric cars. Why is that? Actuators are same principle, physical principle as e-drive system. You have on an electric motor with some gearbox, usually made of plastic gearbox. For small actuators, for big actuators like electric power steering, of course, is a different story. But all of them have a similar noise behavior as e-drive systems. So we have lots of projects for that as well. And that includes pumps and bearings. What is NVH analysis in production? Well, unlike R&D, there is some special characteristics on NVH systems for production. The obvious one, the first one, is it has to be robust and automatic and fast. We don't have days or hours or weeks to set up the system. So it has to measure in minutes, sometimes even in seconds. And so it has to be fast and reliable. The second thing is that it has to give you a good, no good judgment for the product it's testing. So it has to tell you right away, it's okay and okay. So that's the first thing. So it has a pass-fail limit evaluation. Later on, you want to know, okay, I have too many NOKs. What's the root cause of this? Why am I seeing such a noise phenomenon so often? I didn't see before, I'm seeing now in my production. So you want to have a root cause analysis for that. You want to handle different parameters for multiple types. Probably you are testing different types of products in the same in the same production line. They may slightly vary on the design, but NVH signature is going to be different, and your NVH system in end of line needs to understand that. So if you're testing eDrive system A or B, is slightly different, but with different NVH characteristics. The system must understand that and say, okay, for this unit, I need to test this, and that. Those are my limits, and for the other one, those are different. You want traceability, of course. You want to track down what did I measure in the past. You want to preferably be able to listen to what was measured. So we're talking about noise and vibration. So better listen to what was measured. So with all this data, you can run your production statistics, do some trend analysis, and very important, you can feedback your R&D team on trends you see in production, so you can help your R&D to improve your own product. And last but not least, this is a trend we're going to discuss a little bit more in the later slides. We are starting to use machine correlation and artificial intelligence based evaluation to optimize the process. It's all about smart factory now. So when you think about production testing, it goes beyond just measurement. It can help you turn production from a cost center into a P&L center. So you really want to focus on the profit that you are generating for your corporate. So you're really driving sustainable growth when you take a look on big data in production. Okay, so it always starts with measurement. So we need the measurements. And to do the measurements, you need proper sensors, proper hardware. So the sensors designed for production, NVH, end of line, they differ from R&D. They need to be reliable, designed for being coupled and decoupled from the product under test very quickly. We usually recommend vibration sensors. Sometimes we use also airborne noise sensors like the near field microphone here whenever required. Another interesting sensor is what we call the torsional accelerometer. What Marjorie mentioned before, very important topic, torque ripples. It's on the nature of electric motors. It's on the nature of the thing. So we want to control that, and we can do that in the end of line as well. So the right sensor for that is this one here. It doesn't measure linear vibration, but torsional one, which is a direct correlation between torque and the vibration that is transmitted through the body of the vehicle. So we're not measuring torque, we're measuring acceleration, torsional acceleration. So we know that there is a direct linear relation between torque and acceleration. So we can do the math here. So also a reliable, robust data acquisition system, an industrial computer able to process all this data quickly and store it as well. So in order to detect reliably, or in order to separate OKs from NOK parts, we use a multitude of values in a multitude domains. First one is obviously the time domain of the vibration signal. We use a lot of tools around that. You probably, those working with gears probably have heard about crest and kurtosis. The secret is how you use that. So we have some proprietary algorithms that can separate the noise by rotation speed of each shaft. So we do not only detect the nick in a gear, we can tell which gear has the issue as well. So that also includes other domains, frequency order domains. We do order track. One thing interesting about order track is that sometimes a simple order track is just recording the maximum of each point may lead to false NOKs. You may just surpass the limits in a certain very tiny area of speed that will judge this device under test as NOK, but actually you just don't hear it in the car. So many customers ask our help to to test the energy within a speed band instead of just point by point. Other tools are, for instance, for internal combustion engines, a cycle spectrogram where we track the explosion. Here we can see a 4-cylinder engine. We can see the explosion of each cylinder across as function of the order. And from, long story short, from this picture, we can detect several defects on the engine. Last but not the least, modulation. Modulation is a must tool for actuators, as we mentioned before. We at Discom use a slightly different modulation technique. We can use that, but we learned that there are better ways to do that. But we don't use, for instance, envelope. The reason for that is that envelope is by nature a low pass filter, frequency filter. And for e-drive systems and actuators at higher speed, we want to see also the higher frequencies. So for the root cause analysis, we take all these measurements, all these algorithms, and they are mostly based in what we call the synchronous analysis. This is a proprietary algorithm from Discom. We take the time domain noise signal or vibration signal. We separate according to the rotational speed of each shaft of the product. And with that, we can track everything that can potentially be noisy in the product. So here we see, for instance, a spectrogram from an e-drive system. You can see the orders from the gearbox, the transmissions, each gear. You can see the orders from the electric motor slots and the harmonics. You can also see the fixed frequency components of the inverter. So you see the main frequency and the sidebands, and also the harmonic. I think here is a 10 kilohertz inverter. You can see also 20 kilohertz, the harmonic. So we track everything in the system, every single curve, every single line here. So as a perk here, you can see also the consequence of using the torsional accelerometer. On the right, you see how the torsional acceleration, the TAC sensor can detect the torque ripple there beautifully. How do we evaluate the limits? So how do you say, oh, okay, how can I classify what is good and what is no good? So basically in the lines, you have two major objectives. You want to find parts that are potentially going to be audible inside the car, but also find defects in parts that might limit the lifetime of it. So in order to achieve both of these, we use two limit strategies. The first one are fixed limits confirmed by the drive testing cars. So imagine that you put your e-drive system into the car, you drive it, and then you expect from your gearbox which are the major orders based on the kinematics. So you test on the car, and that's the ideal situation. The vehicle, the driver will tell you which are the limits that you should apply in your end of line for the maximum vibration limit for these gear orders or electric motor orders. So those are the fixed limits. The other ones, the rest of your frequency order spectrum, you want an automatically learned limit. So we have an algorithm that will teach the system based on 100 to 100 samples. We'll teach some limits across the whole spectrum. Why is that? Well, if you think about ghost orders in gears, you never know where they're going to pop up. So you want to make sure that you are monitoring the whole spectrum. Bearing noise. Apart from the 3-4 major bearing frequencies, the ball, pass, outer track frequency, inner track frequency, and so on, bearings tend to have some very complicated noise to detect. They might be quite broadband, so you don't know which frequency range they're gonna appear, but they appear as a broadband noise. For instance, the train frequency, there is no bearing train frequency, but there is it can lead to a modulation of the whole noise. You probably know that the manufacturer of the bearing probably going to give you the modulating frequency, but you never know what's going to be the carrier frequency. So that's why you need to monitor the whole spectrum. So as you know, you usually end of lines or productions doesn't have just one line. You have several ones testing the same product. So here, for instance, you have 4 end of lines, 4 different systems testing the same product, for instance. You don't want to operate all these individual end of lines individually. So you want to set up all the parameterization, all the limits, everything centrally, and then you want to distribute to the same parameterization to each one of these systems. So you do that by a central server, or can be a physical server in your manufacturing plant, or can be in the cloud. So here's your computer. You as an engineer, you set up the whole parameterization, define the limits, etc., send to the central parameterization database, and that distributes throughout your end of lines. As a feedback, these end of lines are going to send you all the results back to this central result database. This is very important because with this, all these results from all end of lines, you are able to draw conclusions from statistical analysis and big data. So it's all about asking yourself, which trouble is going to hit me today? So our experience is the following. If you have NOK parts, the first thing to troubleshoot is to look at the statistical analysis. So is that one case? Is it happening often? How often does it happen? Did we change anything in our production? Did you switch tools? Did you change the operator? Whatever. So we first look at the statistical trends. Discom has a tool. You're going to receive a copy of this presentation. Here you see a link for Discom Data Hub, which is the WebPow core, the tool that we call. This is our statistical analysis to support our customers. This is included, part of it is included in the package, as a matter of fact. So far, so good. What's coming next? What's the future happening now? Is a smart factory. Now you have your production under control, but you know what? I have my eDrive system under control, but what about my suppliers? Can I avoid detecting a defective gear after I mounted it into the eDrive system? Because that's already too late. It's better late than never, but it could be earlier, meaning can I correlate the data that I'm measuring my end of line with the end of lines from my suppliers? This is what we are working in right now. So this is an example here. In the left side, you see this graph. This is a graph of a single flank gear tester. So it's testing one single gear. The red one is a gear with some ghost orders. And on the right side, you see the spectrogram from the eDrive system with this gear installed in it. So you can see that this ghost order appears there, but not always, not across the whole speed range from the eDrive system. The x-axis is the speed range. So it happens only in certain speeds. So if you have the communication between end user, customer, and supplier here, you can exchange this kind of information and optimize your process as well and gain a lot of insight on what's going on. This is a big trend in modern manufacturing nowadays. Another example is data mining. What we see here left is a carpet. This carpet is 3,000 spectrograms from 3,000 eDrive units, gearbox transmission units here. So we kind of take a deviation spectrogram, we filter out everything that happens every time because we are interested only on abnormal things. So we take these 3,000 deviation spectrograms, we kind of sandwich them together, and we make this beautiful carpet here on the right. Then we start seeing some interesting things. For instance, these yellow abnormalities in the beginning on the, I don't know, in the first 100 units here, there was something happened here on this order range. So you start asking yourself, what happened that time? Did we change the honing tool from the gear to a new one? Did we set up our machines wrongly? Whatever. So we start gaining insight from a much broader perspective to your production. The last example is artificial intelligence. So this is especially interesting for actuators. Lots of customers use subjective analysis. So the human hearing separates okay from non-okay parts. How about we have these people judging units and judging okay and okay, but we, at the same time, we measure these units with objective metrics and let the system learn which are the metrics and which are the metric limits that we're going to enable us to mimic the subjective analysis. So we as operators are teaching the system how to think exactly like we do on subjective analysis. This is a great tool for actuators. It's never going to match 100% because, as the name say, it's a subjective analysis. We as human beings change our mind constantly. So subjective analysis is subjective, it changes. The advantage of computers is that objective analysis, that once the input is set up for the same input, it's gonna gives us always the same output. This is my last slide. It's a recommendation, suggestion, if I may. If you want to take this journey about artificial intelligence and big data in production, make sure that you have the knowledge. This is a domain knowledge-driven analysis. It's very important that you have the NVH expertise with you. It's because the software or the programming, without knowing what to search inside your algorithm, it's like trying to walk in a maze blindfolded. So it's not going to happen. So we are here to help you on this topic as well. So I guess that's as much as we had to present. Thank you very much.